Hello, I'm Seema and welcome to part 19 of the chapter Chemical Bonding and Molecular Structure. We have studied the Corson-Lewis approach to chemical bonding. Then I told you about the covalent and ionic bonding, the difference between the two types of bonds. And I followed that with videos on the Vesper model, that is the Vesper theory, that is valence shell electron pair repulsion theory. And in the previous few videos, we discussed the valence bond theory and I explained hybridization to you. It is now time to move on to the final theory, which is known as the molecular orbital theory of chemical bonding. In order to know the molecular orbital theory, let us first see what are the salient features of this theory. I'll deal with the features one by one. I've written them out on the board for you. The salient features of molecular orbital theory, just as valence bond theory is abbreviated as VBT, the molecular orbital theory is abbreviated as MOT. The features of this theory are, what does the valence bond theory tell you? It tells you that the outermost shell electrons, it is these which participate in chemical bonding, and the orbitals of the outermost shell, they overlap. And when they overlap, it results in the formation of a bond. This region, the two electrons which are contributed by both the atoms, they are shared equally in that region of overlap by the two nuclei, and they belong to both the atoms, and thus it helps to complete the octet and chemical bonding is formed. The reason for the bonding, according to molecular orbital theory, remains the same, that atoms still bond with each other in order to complete their octet. But the concept of only the valence orbitals overlapping, that is expanded in the molecular orbital theory. In MOT, it believes that it is not just the outermost shell, orbitals of the outermost shell, or only those orbitals which are half-filled like we talked about in hybridization. They should either be half-filled or they are completely filled in order to hybridize, and then the half-filled orbitals, they overlap and they result in the formation of sigma and pi bonds. The concept of sigma and pi bonds still exists, but the only difference in this here is that molecular orbital theory says it's not just the outermost shell or not just the half-filled orbitals which overlap and result in the formation of the bond. All orbitals, they kind of merge and it results in the formation of molecular orbitals. As we talked of hybridization of only certain orbitals, this says that orbitals of both the atoms which are comparable in energy, for example, if you have two lithium atoms, you have 1s orbital of lithium here and 1s of this lithium. Both the 1s will combine with each other, 2s will combine with each other, the 2p would combine with each other. That is how it goes. All orbitals, they merge with each other. The only thing is that 1s of one combines with 1s of the other, 2s of one combines with 2s of the other, and so on. So let us start with the salient features, and then as we do the details, you would find it's really, molecular orbital theory is very interesting. And it really makes sense, you know, to imagine just half or just a partial atom would combine seems a little difficult to understand. This makes more sense and you will realize it as we do it. The salient features, the first feature is that the electrons in molecules are present in molecular orbitals, just as the electrons in atoms are present in atomic orbitals. Just as atoms have atomic orbitals, the MOT says that molecular orbitals have electrons are present in molecular orbitals in molecules. So just as atoms have atomic orbitals, molecules have molecular orbitals. The second point here is that atomic orbitals of comparable energies and proper symmetry combine. I just told you that if there are two atoms, then 1s of one atom would combine with the 1s of the other. 2s of 1 would combine with 2s. 2px would combine with 2px, 2py with 2py, 2pz with 2pz. So they should not only be of equal energy, they should also have the same orientation in order to combine. Because the idea is again the same, that this is overlapping or merging that is occurring. So these atomic orbitals which combine, only those which have comparable energy, and since all the three p orbitals have the same energy, it means the pz of one can go and combine with px of the other? No. Pz and pz can combine because they not only have the same energy, they also have the same orientation. So we say that they should have the proper symmetry in addition to comparable energies. Why we say comparable energies is because it's not always the atoms of the same element which are combining. The 1s orbital of one element may have slightly different energy from the 1s orbital of another element, an atom of another element. So we say they should be comparable. So they should be comparable and they should have the proper symmetry in order to combine. The third point here is that in atoms, we find that electrons, they are being attracted by one nucleus. So there is only one nucleus that influences the electrons in an atom. So we said there's only one nucleus that influences the electrons in atoms. Therefore, atoms are called monocentric. Mono means one, and centric is they have only one center of attraction. That is the nucleus attracting all the electrons. In a molecule, on the other hand, you have more than one nucleus. If you have two atoms, then you will have two nuclei. If you have three atoms, you will have three nuclei. Four atoms would have four nuclei. So we say that multiple nuclei influence the electrons which are present in a molecule. It's not just one nucleus which is affecting it. All the nuclei would be affecting the electrons present in a molecule. Then the fourth feature here is that the number of molecular orbitals formed is always equal to the number of atomic orbitals that combine. If I say that 1s of one atom combines with 1s of 2, it means two atomic orbitals combined. When two atomic orbitals combine, they result in the formation of two molecular orbitals. So whatever is the number of atomic orbitals that are combining would always be equal to the number of molecular orbitals which are being produced. So it is, again, it's just a redistribution of energy. The orbitals, the number of orbitals remains the same. So we say that the number of molecular orbitals formed is always equal to the number of atomic orbitals combined. The fifth feature is that if two atomic orbitals are combining, then two molecular orbitals would be formed. Now, if two atomic orbitals combine and they result in the formation of two molecular orbitals, one of these is known as a bonding molecular orbital and the other is known as an anti-bonding molecular orbital. So you have, they result in the formation of two molecular orbitals, and the molecular orbitals that are formed as a result of two atomic orbitals are the bonding molecular orbital and the anti-bonding molecular orbital. For example, the 1s and 1s of two atoms, it combines to form a sigma bond. Then you will get two molecular orbitals. One would be sigma bonding 1s and the other would be sigma star anti-bonding. We call it sigma anti-bonding 1s, which means that you get two orbitals. One is the bonding orbital and the other is the anti-bonding orbital. The next feature is that the bonding molecular orbitals, they have lower energy and the anti-bonding molecular orbitals have higher energy. Now let us assume that you have two atoms of hydrogen. Both the electrons are present in the 1s orbital. So both of them have the same energy. But when they combine to form a molecule, then the two molecular orbitals are formed as a result of combination of the two 1s orbitals. One is the bonding molecular orbital and the other is the anti-bonding molecular orbital. This is the energy of the 1s orbitals, atomic orbitals. The bonding molecular orbital, which is formed as a result of this combination, it results in the formation of two orbitals. So if this was the energy of the atomic orbitals, the bonding orbital has energy less than this original energy and the anti-bonding molecular orbital has energy higher. Do you get me? This was the original energy. The bonding molecular orbital has energy lesser than the original atomic orbitals, and the anti-bonding molecular orbital has energy higher than that. But the total energy of both of these would still be equal to the sum of the energies of the two atomic orbitals. So we say that bonding molecular orbitals have lower energy, and anti-bonding molecular orbitals, whenever two orbitals will combine, they'll form bonding, anti-bonding. Bonding has lower energy and anti-bonding has higher energy. And if whatever has lower energy would have greater stability. The seventh point here is that atomic orbital is the probability. How do you define an atomic orbital? We say an atomic orbital is the area or the region in space around the nucleus where there is maximum probability of finding the electrons of that energy. So we say atomic orbital is the probability distribution of electrons around the nucleus. Similarly, a molecular orbital would also be the probability distribution of electrons around not one nucleus but the group of nuclei which are combining. It's the same thing here. We said only one nucleus has influence, and in a molecule more than one nuclei have influence over the electrons. So now the orbitals, also the molecular orbitals, would be the probability picture of finding an electron around a group of nuclei. The last point in molecular, the salient feature is that molecular orbitals, just like atomic orbitals, when we study the molecular orbitals, we find that they follow the same rules of electronic configuration that we do. They follow the Aufbau's principle, that is, the energy of the lowest energy level, molecular orbital of lowest energy level fills up first, and then the electrons keep going to the energy levels that are higher and higher. And then it says, that is Aufbau's principle, it follows Hund's rule of maximum multiplicity. If you have degenerate molecular orbitals, they will first be singly occupied and then the pairing will start, right? So they follow Aufbau's principle, electrons fill up according to increasing energy of orbitals. They follow Hund's rule of maximum multiplicity. If they have degenerate orbitals, they would occupy them singly and then the pairing starts. And finally, they follow Pauli exclusion principle. The Pauli exclusion principle for atoms is that no two electrons can have the same set of 4 quantum numbers. Here also, no two electrons can have the same, we don't use quantum numbers here exactly, but they cannot have the same configuration. Each one has a distinct position in the molecular orbitals, just as electrons had in atomic orbitals. We say in an atomic orbital only 2 electrons are present, and both of these also are different in their spins. Therefore, they can never have the same set of 4 quantum numbers. The same thing happens with electrons in molecular orbitals. Every molecular orbital, just like atomic orbitals, has a capacity of only 2 electrons, and both of these should have opposite spin. Therefore, they would definitely be following Pauli. Each electron has an exclusive identity or an exclusive address in the molecular orbitals. So this is the basic, framework of the molecular orbital theory. In the next video, we'll study about the molecular orbital theory better, and then we'll start applying it to elements. If you found the video helpful, please give it a thumbs up and subscribe to my channel. Recommend it to as many friends as you can. Help me spread the word about them. And please keep returning for more videos in chemistry. And bye-bye for now.